Hey ladies and gentlemen, just going to make a really quick video. I don't have a lot of time this morning, unfortunately, but I'm going to make a really quick video for you virtual physics students about conservation energy. This is what we're going to be working on in class, and I am going to be working mainly on the whiteboard today, I believe, so I'm not going to have a really great way to share that with you guys. I could try to capture it by laptop, the camera, but it just isn't going to do a great job. So I'm going to give you a little kind of mini lecture. Your assignment for today is to complete the simulated lab through PhET. It's an HTML lab, so it should run fine on your computers. I tested it. I have a student laptop that I tested it on, and it appeared to run fine for me. So. But in order to do so, we need to talk about a little bit of background with this kind of energy stuff and the conservation of, well, in this case, total mechanical energy, and how that is going to kind of tie into the skateboard lab. So when we talk about total mechanical energy, first of all, I'm going to abbreviate that as TME, total mechanical energy. And TME, or total mechanical energy, is the sum of the kinetic energy plus the potential energy. And this is totally true in all cases. This is the total amount of mechanical energy. And then furthermore, we're going to extend this and say, well, there's conservation of total mechanical energy in any friction-free system. And so in the real world, total mechanical energy isn't going to be perfectly conserved. Friction is going to eat out some of that energy and throw it off in the form of heat or sound into the rest of the universe, so the system would lose energy. But we're going to go with these idealized systems like we always do, just to simplify things for ourselves while we're beginning to learn. And so we're going to say that this system is friction-free, and that in a friction-free system, then the total mechanical energy is conserved. And by conserved, what I mean is the amount of TME, of total mechanical energy, remains constant. And so that if the total amount of mechanical energy remains constant, then basically all we're going to do is have transformations occurring. If we lose some potential energy, that has to go into being additional kinetic energy, and vice versa. So the typical thing to look at this on is like basically a roller coaster or a ball on a hill. Basically the same thing from physics perspective. And let's say that this hill, I'm going to keep my numbers nice and easy, is 10 meters high. And first off, I want to ask how fast, well, let's do this. How much potential energy at top of hill? Okay, and that's a pretty easy question to answer. So we're going to say that the potential energy is the mass times gravity times height. And so we would have here 10 times 9.8, so we'd have 98 masses. And it doesn't, we're going to see in a minute, it doesn't really matter what the mass is that's going to drop out of the problems. So I'm just going to leave this as in terms of 98 times the mass. Okay? And then we're going to ask, at the top of the hill, we can also ask how much kinetic energy is there. We're going to assume this thing starts at rest. I didn't specify it in the problem, but I will now. So we're saying this object starts at rest. And so that would be the kinetic energy would be 0. Remember, kinetic energy is 1/2 mv squared, and if v is 0, then kinetic energy is 0. And so here we would have the total mechanical energy being equal to that 98 m, 98 times the mass. And we could say, a follow-up question, the next one where we would use this conservation of energy, is to say, well, what about at the bottom of the hill? How fast is this going? And again, we're going to say that the TME is going to remain constant. It's going to be that 98 M. Because we're conserving it. So it's going to stay the same all the time. Once we find it in one place, we know it in all places. And we're going to say that that is, again, equal to the potential energy plus the kinetic energy. In this case, though, the potential energy is the mass times gravity times height. Well, down here at the bottom, we would have a height equal to 0. So mass times gravity times height for potential energy is going to be 0. And therefore, this kinetic energy must be our 98 M. Well, we know that kinetic energy, in this case 98 M, is equal to 1/2 the mass times the velocity squared. We can see hopefully that those M's drop out, and we'll get that V equals the square root of 196. And if I had a calculator, it'd be great. Just a second. Okay, 196 square root is 14. So at the bottom of this particular hill, our item would be moving at 14 meters per second. And we can do this not just at the top or the bottom, we can do this at any given height. Let's say we were looking at how fast is this thing going halfway down the hill at 5 meters. Okay, we can do the same thing. Once we use the top to determine our total mechanical energy, that remains the same everywhere in the system. So again, we're going to say TME equals PE plus KE. And we're going to say the total mechanical energy is still that 98 M that we had before. And now this is some combination of potential and kinetic energy. The potential energy formula, again, is mgh. So that's going to be the mass that we don't know times 9.8 times 5. And then we're going to have the kinetic energy, which has the formula 1/2 mv squared. So we're going to have 1 plus 1/2 the mass, and times this v squared that we're going to be looking for. That's what we're solving for. How fast is this thing going at 5 meters down the track? Okay, so we're going to have here, notice m is in every term, so we can divide it out from both sides, and these things act inconsequential. The mass is inconsequential in these particular problems. And so we're going to get the 98 equals 49, half of 98, plus 1/2 v squared. So we're going to subtract 49 from both sides. We'll get 49, but then we're going to multiply by 2 on both sides. And so we're going to end up back with this 98 equals v squared, or v equals the square root of 98. And we would find that at 5 meters down the track, the velocity equals 9.9 meters per second. And so conservation of energy is a super powerful tool for us to find these velocities in friction-free environments, because it's so much easier than kinematically trying to solve these problems. Sure, you could solve this kinematically. You certainly could. You could look at a delta y being 10, an acceleration in the y being 9.8, and a v naught in the y being 0, and you could find vf that way, and what it is at the bottom of the hill. So you certainly could approach this kinematically, but these type of problems are just more easily solved through an energy conservation standpoint, so I would encourage you to look at things from that standpoint. I know this is really brief little video. Hopefully, I think this gives you enough to successfully manage the lab. If it doesn't, please contact me and I'll see if I can't find some moment during the day to do a quick supplemental video. But I am essentially out of time right now, so I hope this is enough. I look forward to seeing you, ladies and gentlemen, back in the classroom, and I hope you're having a wonderful day.